Alright, so we're going to talk a little bit here about graphing quadratics. And I just want to remind you that a quadratic is any function of the form f of x is equal to a x squared plus bx plus c. Okay? And when we write this, we say that a, b, and c are real numbers. So these are just, they aren't actually letters that go in there. But, you know, this might be 5x squared plus 3x plus negative 2 or something like that. The only condition on a, b, and c here, other than them being real, is the fact that a cannot be 0. You can imagine if a was 0, this would go away, and you'd have something like 3x plus 2. That's not a quadratic function. At that point, that would be a linear function if you had something like that. Okay, so that's what a quadratic function is. Just want to give you some examples. So what if I gave you something like, I gotta scroll up here on my notes. All right, what if we did something like negative, all right, so examples. So what if we had something like negative 3x squared plus 6x plus 12. Oh, put that in blue there. Okay, so this is a quintessential example of a quadratic function. And what's nice is that it's already in what we call standard form. So we've got the x squared part first, and then we have the x part, and then just the number. Okay, so that's an example of a quadratic function. We'll give you some more. So how about, what if we had 0.12 x squared plus 3.1x plus 4.79. That right there is a quadratic function. It's not pretty because it has decimals, but as long as these are real numbers, they're okay. All right, what about if we had something like x minus x squared? That's a quadratic function. You might have to move it around a little bit and change it to get it into what we would call standard form, but that's fine. We can do that. What would the number be that goes in front of the x squared term? I'm going to say it would be a negative 1. We don't really need to write negative 1. You can just say negative x squared. But that would be that. And then what is the number that comes in front of the x? I'm going to say it would be 1x. We only have 1x right here. And then what is the blue number? Well, there isn't actually a blue number, but if you think about it, if there isn't one, and you could add 0 and it would be the same thing. So this function right here, x minus x squared, it can be rewritten as negative 1x squared plus 1x plus 0, so it's a quadratic. All right, number 4, x squared plus 2. So again, it's lacking one of the terms. We're used to having 3 terms, but that's okay because this is essentially 1x squared plus 0x plus 2. Okay? So those are some examples of quadratic functions. What I want to do now is go to another problem and graph one. Okay, so let's say we've got a quadratic function here that is y is equal to x squared minus 4x plus 7, and they want us to graph it. The easiest way to do this, especially if you're not allowed to have a calculator, is to actually create a table of xy values, and then from that table fill out the table, and then you can graph each coordinate pair. So generally what I like to do is I'll start kind of with x is equal to 0. What's nice about 0 is that you can plug in 0 and 0 here really easily, and the y value instantly I know is just 7 because this is 0 and this is 0, because, you know, 0 squared is 0, 4 times 0 is 0. So 0, 7 is a good starting point. So if we plug in 0, we know we're going to get 7. I'll actually write it out because I'm going to do it for the other ones here as well. So okay, so if we fill this in here, we're going to say that we're going to do 0 squared minus 4 times 0 plus 7. Okay, so 0 squared minus 4 times 0 plus 7. That's just 0 minus 0 plus 7, which is just 7. And let's write that in orange there. So that's 0 minus 0 plus 7. So that's 7. Okay, cool. So the y value there, when we plug in 0 for x, is 7. And now, there's really no perfect set way to do this, but what I'll do is I'll just kind of guess and check. So, like, I'm going to try 1 now. Maybe 1 won't fit on the graph. I'm not sure, but I'm just going to try it and see what happens, because it's right next to 0. And typically quadratic functions, especially when you're close to what we call the vertex, which we'll talk about in a minute, they don't move a whole lot. If you're far away from the vertex and you scoot over 1 with the x, sometimes the y value changes dramatically. So, okay, so we're going to do the input squared minus 4 times the input plus 7. That's what this function tells us to do, where in this case we're worried about an input of 1. So if we do 1 squared minus 4 times 1 plus 7, we would get 1 squared is 1 minus 4 times 1 plus 7. So 1 minus 4 is negative 3 plus 7 is 4. Okay, awesome. So that's a totally manageable point. And let's just keep moving here. Let's try 2. See what happens. All right, so if we plug in 2 for x, we will get 2 squared minus 4 times 2 plus 7. So 2 squared minus 4 times 2 plus 7. So that's going to be 4 minus 8 plus 7, which would give us negative 4 plus 7 would give us 3. So when we plug in 2 for x, we get 3 for y. What about if we plug in 3 for x? And we'll just keep doing this. I usually like to get about 5 points, 5 xy coordinate pairs here before I graph. I also like to check and see if there's any symmetry, which I'll explain here in a second when it pops up. Okay, so we're plugging in 3 now for x, so we're going to do 3 squared minus 4 times 3 plus 7. So 3 squared minus 4 times 3 plus 7. 3 squared is 9 minus 4 times 3 is 12. Oh, I'm writing in white again. So that's going to be 9 minus 12 plus 7. That's negative 3 plus 7. That's going to be 4. So we'll put a 4 here. And let's try 4 here for x and see what we get. All right. 4 squared minus 4 times 4 plus 7. You can see this can be a lot of work sometimes. All right, 4 squared is 16. Minus 4 times 4 is 16 plus 7 is equal to 7. So I mentioned symmetry a second ago, and what you'll notice here is if you look at the inputs and the outputs have a really nice symmetry. It's 7, 4, 3, 4, 7. It's like it repeats itself backwards when you go down here. And this happens with parabolas. They're symmetrical. So let's go ahead and graph this and see what it looks like. So I'm going to take this first point here at 0, 7. So I'm going to go to 0 for x and 7 for y. So 0 for x, 7 for y puts us right here at that point, okay? So that point right there is on the parabola. When we graph a quadratic function, it's called a parabola. All right, the next point is at 1, 4. So when x is 1, y is 4. The next point is when x is 2, y is 3. The next point is when x is 3, y is 7. Or sorry, when x is 3, y is 4. And when x is 4, y is 7. I'm going to do one more point here just to show you, just give you a little bit more of a feel for what this parabola looks like. So let's try 5 here for x. So we'll do 5 squared minus 4 times 5 plus 7. 5 squared minus 4 times 5 plus 7. 5 squared is 25 minus 4 times 5 is 20 plus 7. So that's going to be 5 plus 7 is 12. So the output there is 12. Okay, so let's go ahead and graph that. When x is 5, y is 12. Wow, that's way up there. And let's actually use the fact that we know that it's symmetrical here. So, in other words, this is what we call the vertex right here. If you find a point just to the right of the vertex, the point just to the left of the vertex will be the same distance horizontally, and it'll be the exact same y value. So you'll notice that these two are the same, these two are the same. What's nice is that these two, of which only one is pictured, are the same. So, and if you don't believe me, go ahead and plug in -1 into the equation, and you'll find that it returns 12 for y. Okay, so we've got a parabola here. We're now able to go ahead and just sketch a rough drawing of this, and so we'll go ahead and do that here. So we'll just go this way. It kind of curves up a little bit. It can be a little tricky to get your parabola to go right through every point. That's not bad there. Okay, so we have graphed not every point on this parabola. There's actually an infinite number of points technically, but we've got, how many do we have here? 7? Yeah, so we got a pretty good start here. I guess technically we have 8 points. But anyway, what I want to do now is I want to talk about the features of this graph. And then I want to make a few general observations. So the features of this graph, which are down here. So the maximum, minimum, the axis of symmetry, domain, range, the intervals of increasing and decreasing. I just want to fill those out. So those are some helpful features to know about a parabola, especially when you get into real-world applications. Like if you have a graph that reaches a maximum point, that might be the highest point of revenue that your company is able to generate. So you would want to know where that point is. You also might want to know, hey, where is the function going up? Like as we move from left to right, where is it going up? Where is it going down? All right, so the maximum or minimum. So I have max/min here, and the reason for that is because some parabolas create a maximum point, a highest point. Some parabolas create a minimum or a lowest point. This one has a minimum, okay? And that minimum occurs right here. This is the lowest point on the parabola. So what we're going to do is we're actually just going to list the coordinate pair of that minimum value there. So that's going to be at 2, 3. So the x value is 2 and the y value is 3. The axis of symmetry, this is kind of cool. Every parabola has an axis of symmetry, and it's a line that goes right through the middle of it, goes right through the vertex there. By the way, this right here, this point, this bottom point is the vertex. If it's the top point of a parabola, then that would be the vertex. But this one has a bottom. That's the vertex. This axis of symmetry is kind of almost an imaginary line that you can draw right through the vertex going straight up and down. And it's just, when they ask for the axis of symmetry, they're just asking for the equation of that line that I just drew there. So that dotted green line there, the equation of that line would be x is equal to 2. It's just a vertical line, and it happens to be right here at 2 for x. So that's the equation for your axis of symmetry. The domain of this function, remember the domain is all of the possible values that we could plug in for x, and the range is all of the possible values that we could get for y, the y values, okay? The domain on this function is all real numbers. In other words, we're not really limited by what we can put in for x. We can put in positive numbers, we can put in 0, we can put in negative numbers. Really any number you can possibly think of, any real number, you could plug in here for x and it would work. So what we're going to say here is we're going to say that the domain is all reals. Some people will write the bold-faced R that looks like that. That's fine. I usually like to give it an interval notation, so I'll say anything from negative infinity to positive infinity, I could feasibly plug in here for x as an input, and it would work. Okay. Generally, for quadratics, unless there's some weird restriction, like it's a piecewise function, the domain will be all real numbers, because you can plug anything you want into a quadratic function. There are some functions where you can't plug some things in. Like if we took the square root, you can only take the square root of positive numbers and get a real number result. So, but we'll get into those later. Okay, the range is all of the possible y values that come out of this function, and it helps to look at the graph for this. If I just looked at this, I would have a really hard time telling you what the range is. But if you look at the graph visually, what happens here is that this goes up forever to the left, and this goes up forever to the right here. And the lowest point that this parabola reaches is actually right here. It's when y is 3. So if you tried to find a point on this parabola where the y value is 2, like down here, you would never be able to find it because the y values never come lower than this point right here. And if the range is asking what are all the y values that this function hits, then what we're going to say is that the range is including 3, so starting at 3 up until infinity, every y value between 3 and positive infinity will be hit by this function at some point. Okay, will the y value ever be 87? Sure, yeah, somewhere way up here. Okay, you just have to go for a little bit, but it would eventually happen. All right, where is this function increasing? Okay, so what this is asking is if you were going to follow this function from left to right, so we're going from left to right here, the question is where are the y values going up? Okay, so if we follow this function, I'm going to say as we go from left to right here, we're actually going down. Down, down, down. You can almost imagine like a roller coaster if somebody was riding from left to right. The parts where they're going down, that's where the function's decreasing. Okay, right here I'm going to say the function is neither increasing nor decreasing here. You would actually have to use some calculus to show that it is the slope right here is actually completely flat at 0. But as soon as we start to get here, we are now, as we go from left to right, we're going up, so we're increasing. Okay, so just to highlight this for you, we are increasing here and we're decreasing here. I like to color code like red for decreasing, green for increasing sometimes. Okay, what we do when we give our answer here, this is a little weird, is we give the x coordinates of where we're increasing. So in other words, there's a point right here where we're neither increasing nor decreasing, and then everything over here, like all of these x values over here, if you pick any x value there and you follow along the function, like let's say at 2 here, what's happening at 2? The function is increasing. It's going up as we move from left to right. So what we're going to do is, instead of giving the y values, which I think would be a little more logical, we actually give the x values here. So we're going to say that we're increasing from 2 to infinity. And we're not including 2 here because we're not actually increasing at 2. We're not increasing or decreasing at 2. All right, how would we give the interval where we're decreasing now? So I'm going to say that the interval where we're decreasing, if we're just looking at the x's, is anything to the left of that axis of symmetry there. So it's all of these x values over here, where if you follow this from left to right at any one of these x values over here, you're going to be going down, you'll be decreasing. So what we'll say here is all the way back to negative infinity, we happen to be decreasing, and then that happens until we get to 2. So if you're anywhere between negative infinity and 2 as far as x values go, this function will be coming down. But if you're anywhere between 2 and infinity for the x values, this function will be going up and increasing. Okay? All right, some quick general observations here about parabolas and quadratic functions. These aren't super important, but they're just kind of helpful to know. So first thing that I want you to observe is that they tend to have a U shape. They will always have a U shape. Sometimes they're upside down, so it looks more like an N instead of a U, but they will always have that U shape. Another thing is just what I said there, they may open upward or downward. We'll just say up or down. Is downward a word? I don't know. And they're symmetrical, which I've already said a few times, but it's worth making a little note about it. Okay, let's try another example where it opens down. Downward, down, I don't know. All right, so here's our function. So we have y is equal to negative x squared minus 4x plus 2. And I'm going to do the exact same thing that we did last time. I'm going to make a table, make an xy table. And again, I'd like to start at 0. Now, you're not going to know why I'm doing this right now, but just trust me if you're taking notes here along with me, I'm going to actually start down here, and you'll see why here in a minute. I'm going to put the 0 there because I want to be able to get to -1 and -2 in those numbers here in just a minute. But for now, let's try 0. So if we plug in 0 into this function, the function tells us to do negative times the input squared minus 4 times the input plus 2. In our case, we're plugging in 0. So this is just 0 minus 0 plus 2, which is 2. Okay, we're going to be running out of room here. I'm going to move this graph over just a little bit. Okay, so when we plug in 0, we get 2, which is great. What I would generally do next is I would try 1. So let's do 1. Let's feed 1 into the function. So -1, oh, I don't want to put that there. -1 squared minus 4 times 1 plus 2. That's going to be equal to, all right, let's do it. So this is really important, by the way. A lot of people goof this up. You have to follow order of operations here. Remember, it's parentheses, then exponents, then multiplication. In this case, we've got parentheses, and we have an exponent here. So you need to do the exponent first. So you're going to do 1 squared, then you will multiply by -1. That's what that negative sign is there. It's multiplication. Okay. So this is technically going to be -1 because what happens here is you do 1 squared, which is 1, and then you multiply by a negative. So you'll get -1 there. A lot of people, a ton of people put +1 there because they think that you're supposed to square -1. You're supposed to do -1 times -1, but that's not what that says. All right, so -1 minus 4 plus 2. That is -5 plus 2 is -3. Okay, so we get -3 when we plug in 1. And I'm going to move the max min stuff down a little bit. Let's try, what if we try 2 for x? So we've got -2 squared minus 4 times 2 plus 2. So we'll fill that in, -2 squared plus, minus 4 times 2 plus 2. So that's going to be -4. So you do 2 squared is 4, and then you multiply by -1. And then that's going to be minus 4 times 2, which is 8, and then plus 2. So that's going to be -4 minus 8 plus 2, -10. And so what you'll see on these, when you have a quadratic function, you know it's a quadratic function. What you're going to see on these is they start to change, and then they really change quickly. So this was 2 to -3, which is a jump of 5. This is -3 to -10, which is a jump of 7. As you keep going down here, like if we went to 3, it jumps even further and it starts to jump faster. Okay, so the change in the y value gets bigger. So what I'm going to do is, instead of continuing going down that route, because I don't have a whole lot of room on my graph here, it only goes to -11. What I'm going to do instead is I'm going to start to work my way backwards. I'm going to try -1 now in my function. So I've got -1 squared minus 4 times -1 plus 2. So fill in those -1s there. Okay, so this now is going to be, okay, so many negatives here. If we do -1 squared, that would give us +1. And then if you multiply by negative, you'll have -1. So 3 negatives makes a negative, I guess. Okay, minus 4 times -1, that's going to be plus 4 plus 2. -1 plus 4 plus 2 gives us 5. Okay, so this is 5. So we're going up now instead of down. That's interesting. Let's try -2 here. All right, -2. Oh, I'm not supposed to fill that in. -2 squared minus 4 times -2 plus 2. So -2, -2. All right, what is this? This would be -4 plus 8 plus 2. -4 plus 8 plus 2 is 6. So we're still going up, but we're not going up very much. I wonder if we're going to start to turn around here on the next couple x values. I bet we will. All right, -3 squared minus 4 times -3 plus 2. -3, -3. Okay. So this will be negative 9 plus 12 plus 2. So negative 9 plus 12 plus 2 would give us 5. Uh-oh, so we're going down again. And this is good. This means we've reached the vertex. In all likelihood, this is probably the vertex right here. All right. Let's do one more. So we'll do negative 4. So we'll do negative 4 squared minus 4 times negative 4 plus 2. And this is going to be negative 16 plus 16 plus 2. And that gives us 2. And so what you'll start to see here is here's the symmetry that we were talking about, right? 2, 5, 6, 5, 2, negative 3, negative 10. I bet if we went up to negative 5 and negative 6 here for the x values, we would get negative 3 and negative 10 for those, respectively. Okay, so let's actually go ahead and graph these points here and see what this parabola looks like. So, all right, negative 4 comma 2, so that's the first pair there. We'll just go from top to bottom here. All right, so negative 4 comma 2. That's going to be right there. Negative 3 comma 5 is going to be right there. Negative 2 comma 6 is going to be right there. Negative 1 comma 5 is going to be right there. 0 comma 2 is right here. 1 negative 3, 1 comma negative 3 is going to be down here. And 2 comma negative 10 is going to be down here. And just for symmetry purposes, since we have a point here, I'm just going to bring it over and drop another one there. And since we have a point here, I'll bring another one over and drop it right there, since we know that these are symmetrical. Okay, and now we'll go ahead and graph this. Alright, so we'll just kind of draw a curved line there. Yeah, I messed that one up. Let's try that again. Nope. Take 3. Third time's a charm, right? I missed a little bit there on that one, but you get the idea. It's kind of hard to always be changing, like, the steepness of the... First it's not very steep, and then it gets really steep. Okay. So there is the graph of our quadratic. And now what we're going to do is fill out the max-min axis of symmetry stuff. So let's look at that stuff. All right, does this have a maximum or a minimum point? It sure does. It does all the way up here. So that point was at negative 2 comma 6. So all we're going to do is list that. Negative 2 comma 6. And that's the vertex, by the way. That's what that is called. The axis of symmetry. So there is a line that goes right down the middle here. And the question is, what is the equation of that green dotted line there? That green dotted line equation is going to be x is equal to negative 2, because that's the x value right there. Negative 2. All right, and then the domain on this function, the question is, are we restricted in any way on what we can put in for x here? No, you can plug in anything you want. You can square it, subtract 4 of it. That's fine. So the domain here is going to be all real numbers. Basically, we're just going to say parenthesis, negative infinity, comma, infinity, parenthesis. So you can put in anything you want. How about the range? So the range deals with the y values. What y values are covered by this function? If you look at the function visually, again, I would not recommend looking at this. There's no way for me to know, just glancing at this, what the range is. I mean, there is, but it's complicated. Just visually looking at this, it looks like basically everything from 6 down is covered. And so what we're going to do is we're going to say, be really careful here. The order is really important. A lot of people want to say 6 to negative infinity, but the problem is that you need to actually list the lesser number first. And negative infinity is technically lesser than 6. Even though infinity is a bigger number, the fact that it's negative means that it is less. So what we're going to do is we're going to say from negative infinity up until 6. Now, should we include 6 in the range? Does the y value ever actually equal 6? So if we come over The y value does equal 6 there, so yeah, we should include it. So let's put a bracket there instead of a parenthesis. So put a bracket there instead of a parenthesis. That means we're going to include the 6. All right, where is this function increasing? So if we look from left to right, if we follow this along from left to right, are we going up or down right now? We're going up, which means that the function's increasing right here. So on this portion of it, it's increasing. It starts decreasing right about here. So it starts going down. So what we're going to say is, if we're just looking at the x values, I'm going to say that we are increasing for this entire green area right here. Any x value you pick over here, if you're following the function along, even all the way down here, if you're following it along, you're going to be increasing until you hit right here at -2. Okay, so I'm going to erase our highlighter there. And our answer here is going to be we're increasing all the way back to -infinity for x until we hit -2. And I don't think we're actually increasing at -2. I don't think we're decreasing at -2. It's just where we level off, and we're doing neither, basically. So I'm not going to include -2 there. Notice how I put a parenthesis there for that one. Okay, how about decreasing? So decreasing, I'm going to say starting at -2 all the way until infinity. So if you pick any x value to the right of this point right here, anything over here, you're going to be decreasing as you go along these x values. So that's where we're decreasing. Okay? All right, so that's that. I wanted to make some helpful observations for you about the a, b, and c values in standard form. So remember, the a was the what we call the leading coefficient. So it's a x squared plus b x. That green is off. Let's get the actual green. Plus bx plus c. So that's just kind of a standard quadratic. Remember that a, b, and c can be negative. But there are some really helpful things about a, b, and c that I want to point out to you. All right, and the first one is, if a is positive, so if that leading coefficient there, if a is positive, the parabola, or the quadratic function, opens up. It'll always open up like this. If a is negative, I think you can see where we're going with this. If a is negative, the parabola opens down. The parabola opens down. So it'll have a general shape. It'll look kind of like this. That's a terrible parabola. It's like all jagged, crooked. There we go. That's a little better. Okay. Next thing that's super helpful for you, especially, this will help you as you're making your table. Next thing I want to point out is the vertex. In other words, the maximum or minimum value always occurs, and I spelled that wrong. The vertex always occurs at, and this is just so interesting that it does this, it always occurs at -b divided by 2 times a. And if you actually go back to our function and you look at it and you think about what -b over 2a would be, so if you come over here, in this case, our a value was -1 and our b value was -4. And if you actually do negative, here, I'll color code this for you. If you do -b over 2 times a, watch this. Watch what happens. you'll get 4 over negative 2, which is negative 2. And so what happens here is that this is the x value. This right here is the x value of the vertex, which is totally true on this function, right? We're at negative 2 here, and that's where the vertex occurs. So we'll go back and we'll say the vertex occurs at x equals negative b over 2a. All right, so we got that. And the last thing I want to point out to you, kind of helpful, is that the y-intercept and this is just the value when x happens to be 0. Okay, so that's the y-intercept. The x-intercepts are when y is equal to 0, but the y-intercept is when x is equal to 0. This occurs, actually, this literally is the number whatever c is. So whatever c happens to be in your function, that's the y-intercept, okay? And you'll notice this here on our function. I'll zoom out just a touch more, okay? Our c value was 2, and if you come over here, the y-intercept was 2. And this kind of makes sense. If you plug in 0 for x, you'll get negative 0 squared minus 4 times 0 plus 2. And so that guy right there will be the y-intercept, and so it'll just be at 2 there. So these right here will always be true for any quadratic function that is of this form, ax squared plus bx plus c. All right, I hope that helps. And one last thing I wanted to do here was talk about how to write the function in standard form if you have a quadratic. This may not look like a quadratic. I mean, it kind of does because it has the square there. But this is what we call vertex form, which we'll talk about later. So we want to talk about how to just get something from vertex form into standard form. And all we're going to do is we're going to multiply this out until we get it to look like ax squared plus bx plus c. That's standard form. Okay, so when we do this, what I'm going to recommend is that you actually multiply the x plus 2 before you multiply the negative 3. And that's not a recommendation. That's a requirement according to the order of operations, right? Parentheses, exponents. So this exponent occurs before the multiplication by negative 3. So what I recommend doing is rewriting it as negative 3. And then you're going to take x plus 2 and multiply it by itself. That's what it means to square something. So this is where we're going to have to do everybody's favorite thing, which is multiplying two binomial expressions. And I'm going to get a little better color here for you because that orange and red, they look very similar. So I'm going to do the yellow things first, then I'm going to do the red things, then I'm going to multiply the green things, then I'm going to multiply the blue things. Okay? So we're going to have negative 3 times, when you do x times x, that gives you x squared, plus when you multiply the, not the red things, the yellow things. So x times x is x squared, and then plus the two red things, x times 2, that'll give you 2x. And then the green, 2 times x gives you another 2x. And then the blue, 2 times 2 gives you 4. So that's this little rainbow thing here. This is what you get when you multiply x plus 2 times x plus 2. You're more than welcome here if you'd like to take the negative 3 and distribute it to everything. But I like to simplify inside the parentheses a little bit first. So I'll write this as negative 3 times x squared plus, let's see, 2x plus 2x makes 4x plus 4 plus 5. Okay, so now we're here, and we're almost done. Let's go ahead and distribute that negative 3. So everything inside this parentheses is going to get multiplied by negative 3. All right, equals equals. I keep forgetting my equal signs. This is going to be negative 3x squared minus 12x, getting the minus 12x from doing negative 3 times 4x. And if we do negative 3 times 4, we will get minus 12. So that's everything in the parentheses there, and then don't forget the plus 5 here. And then from here, we've just got negative 3x squared minus 12x, and then negative 12 plus 5 would be negative 7. So this right here is the exact same as this right here. They're just written in different forms. This one's called vertex form. This right here is called standard form, which is just the ax squared plus bx plus c.